at the School of Mathematical and Computational Sciences at Indian Association for the Cultivation of Science. He earned his PhD in computer science and engineering from Jadavpur University, following dual master's degrees in computer sciences and in computer and electrical engineering from Louisiana State University, USA, and a BE in electronic and telecommunication engineering from BE College, Shibpur, which is now known as IIEST. He had a brief postdoctoral research stint at Queen's University, Belfast. His research spans graph algorithms for large-scale social networks, graph-based NLP and generative vision models in computational biology, etc. He has recently published in prestigious venues like STM, CIKM, ECIR, PAKDD, KAIS, Nature Communication, etc. Before joining IACS, he taught at Heritage Institute of Technology, where he received the Best Teaching Award in 2015. Dear sir, handing over the session to you.
So thank you and welcome back after the tea break. So we will start with the same author. The first two papers we are going to have are going to be online. So I'm just going to read out the name of the author and the title of the talks. So the name of the author is Yoshihiro Maruyama, if I'm right. He's from School of Informatics, Nagoya University, Japan. And the first talk's title would be Top K Exterior Power Persistent Homology, Algorithm Structure and Stability. And the second one will be Algorithm for Interpretable Graph Features via Motivate Persistent Cohomology. We will come to that after the first talk. Let us have a look at the first talk. Thanks.
Hello everyone, I'm Yoshihiro Maruyama from Nagoya University. I'm talking about top K exterior power persistent homology, algorithm structure and stability. So given a persistent module M, we consider a barcode V of M, which records when single features are alive. By contrast, the exterior power lambda IM records when I independent features are alive together. So it records concurrency information. In applications, we want a compact, fixed-length, stable summary. Naively computing B lambda IM is expensive. Even for I equal 2, there are so many pairs. So the goal of this talk is that given only V of M, compute the k longest bars of V of lambda IM exactly with multiplicity while avoiding full enumeration. The key fact is this one, exterior power interval calculus at the barcode level. This one says lambda I bars are just intersections of input bars. Pick I bars, then the corresponding lambda I bar is their intersection. So for I equal to, we are ranking pairwise overlaps by length. The calculus is simple, but the number of intersections is not. In high overlap regimes, this one becomes a bottleneck. Yet, top K only needs a front end of this huge multiset. This is our strategy. We exploit two pieces of structure. Every intersection has a unique moment of birth, anchor. For a fixed anchor, candidate lengths form a monotone stream that we can merge with a heap. We process all birth deaths in increasing time. at times death before birth. Among equal time births, fix any total order. Given I bars whose intersection is non-empty, their lambda I bar begins at T star, maximum of this one, the latest path among the chosen bars. At time T star, several bars may be born. The one processed last is the anchor R star. All other chosen bars must already be alive just before B sub R star. Just before the birth of bar R at BR, we let AR, this one, and CR defined this way. And we order AR by death time, largest first in this way. And length profiles, if the last chosen neighbor dies at DRJ, then the intersection cannot last longer than this one, LRJ, defined as the maximum of these things. The intuition is that as we allow worst ranked neighbors, the earliest death gets earlier. So LRJ is non-increasing this way. Fix an anchor R, and we choose I-1 neighbors from AR and write their ranks in the sorted by this order as S, this way. The resulting lambda I interval is this one. Why does this matter? All choices with the same largest rank J as max S have the same length LR of J. So we can group many combinatorial choices into one length plus one multiplicity. Multiplicity is this one. And we have this decomposition theorem. B of lambda IM is a union of weighted monotone streams in this way. Each anchor R contributes a monotone stream. And because each anchor system, each anchor stream is already sorted, non-increasing, top K is like merging M sorted lists. So we maintain a max heap of current stream heads Rj keyed by LRJ. We repeatedly pop the largest head Rj, emit its value in bulk with multiplicity until we reach K outputs, and we advance that stream to Rj plus 1 and push it back if still positive. Why is this correct? No unseen element can exceed its stream head, so the global maximum among all remaining candidates is always in the heap. How do we query LRJ first? To compute LRJ, we need DRJ, the largest death time among bars, alive just before BR. We coordinate complex distinct death times and sweep events in time order, maintain a multi-set of alive deaths, and we make it persistent. That is, at each birth R, store a snapshot root TR representing AR. And using TR, query this one to get DR of J in O log M, then compute LRJ this way. Yeah. Then we have this one, exactness and running time. The grouped best first algorithm outputs the exact top K multiset of lengths of the black code of lambda IM in O of M plus K log M time using OM heap space plus OM log M persistent nodes. This is the first result. And the second result is a lower bound. Even for I equal n, k equal 1, any comparison-based method needs omega of m log m comparisons to compute the longest lambda2 overlap from unsorted endpoints. The third result is stability. Exterior powers are 1 Lipschitz. Top k length vector is actually 2 Lipschitz in this way. While the factor 2, bottleneck matching moves each endpoint by at most epsilon, so length change by at most this one. So top k length vector is 2 Lipschitz. We also did some experiments to demonstrate the advantage of top k algorithm. Setup will report end-to-end load time for a fixed query on barcodes. Baseline enumerates all pairwise intersections, computes the full of this one, and then selects the top k length. Our method performs grouped best first over anchor stream emitting lengths in bulk via binomial weights. It touches only as many candidates as needed. In every round, top k multiset agrees with the baseline up to rounding. And we have experimentally verified that our top k algorithm work faster than the baseline, enumeration baseline. Intuition is this, more overlap means this one grows fast, but top k stays fixed. Best first avoids the baselines, enumerate everything cost. Yeah, so this is a summary. Lambda I captures coexistence of I features. And every lambda I interval has an anchor candidate from weighted monotone streams. And top k is a heap merge of stream heads giving near output sensitive time. And we have this stability result. The top k length vector is stable to Lipschitz. Okay, that's it. If you have any question, please email me. The email address is this one. Okay, thank you so much.
Right. So if you could display the email ID once again. So if anyone is interested.
So much. If you
I wish the author was here because
that's
you guys
it.
might have had
If you have any
a
question,
few questions or
please
two.
email
Yes.
me.
No.
The email
Email
address
ID.
is this
Can
one.
you not? Yeah, that's fine. You display. It's not a problem. So if you have questions, please send it to him. All right. So there is no scope of discussions about question answering as such. So we will proceed to the next talk, and I'll read out the title once again as I did for the first paper. So the title for the second talk would be Algorithm for Interpretable Graph Features via Motivic Persistent Cohomology. All right, thanks. If you could kindly start the presentation, please. think we're done with the talk. So any comment that you would like to have from the audience? Anyone maybe? Okay, all right. If that's not the case, then you are next, Uros. Next. Okay, because your name was last. So wait. So I just need 1 minute of extra time from the organizers to tell that Uros and I met in the same Icaa conference 11 years back. So 11 years back, we met for the first time, and then we, I think, collaborated on one paper, right?
Yes.
So we kept in touch and we collaborated in one paper. And after 11 years, we meet again. So let us hear it from Uros Sives. I think, Uros, you were a PhD student at that point of time in University of Ljubljana.
Yes.
So University of Ljubljana is a very famous Central Europe university. He was a PhD student there at that point of time, and now he's a faculty member over there. So now he's going to talk about small, uniquely satisfiable patterns. A very small title, but big things underneath. So
Okay, thank you, Partha. I have to disappoint you. It's 12 years, I think, not only 11.
2014?
Yes.
2014. Yeah. Now it's 16. Yeah, the year two.
It's okay. A few years. So thank you very much. I have a small title about small, uniquely satisfiable patterns. I have basically 3 points I would like to tell you. The first one, a little bit of motivation, what I'm even talking about when I talk about patterns and satisfiability. You can already know about what I mean by the name. Building a catalog of these patterns because I believe they might be or they will be practically useful in the future for building better software. And the third point, I want to show that this is actually practical by showing that these patterns appear in practical instances of problems that I'm dealing with. So what I'm talking about is this. I'm talking about satisfiability, so the SAT problem, which I think I don't have to introduce to you. Oh, it works. Unique, I mean a formula, a logical expression that has only satisfiable assignment. Okay, and I mean I want to generalize the concept of a unit clause. So if you see this formula here, X4 is unit clause. So I will be always talking about conjunctive normal form of this expression and a clause that has only one variable, unit clause, and it has a special place in SAT solvers because when I have a unit clause, I exactly know that this variable has to have a value 1. Expression has a value 1, right? And this has a cascade of consequences, namely if the negation of X4 is present in a clause, I can remove this occurrence, and whenever X4 is present in a clause, I remove the whole clause. This has a cascade of consequences, and this operation is called unit clause propagation. The core of every SAT solver, every software that finds solutions to this problem, and it spends mostly like 85 to 90% of time SAT solvers spend doing unit propagation. So it's an important concept in SAT solvers. So I want to find a generalization of this unit clause, something that has a similar consequences for the expressions, and this generalization could be a different way or an extended way of doing unit propagation. So the second goal is to provide a property or a metric, a property of SAT instances, which could help classify them. So this is another information that SAT solvers might use, because for different classes of instances, SAT solvers apply different tactics. So it is helpful to distinguish different types of SAT instances. And I'll show you that this might be one of the properties that might help, right? And the third thing, this concept might be useful for static preprocessing. So a lot of for static preprocessing of SAT instances exist, and this might be one of them that might also help in certain instances, right? So these are the three goals that I have for this work, right? So formally, a satisfiable expression is an expression or a formula. I use these terms endlessly, with exactly one satisfying assignment. And this is a known problem. It's also very theoretically interesting. It has its own complexity, consequences, whatever, but I'm not interested in theoretical aspects. I'm interested in just the practical aspects of this thing. And I want to generate this kind of expressions. Because there is no systematic way of generating them. We have to search for them. So we have to generate a lot of instances and check for each of them if it's uniquely satisfiable or not, right? So as I said before, I want to build a catalog of small uniquely satisfiable patterns, and I want to explore how these patterns occur in real life or realistic instances. I will use instances from SAT competitions that occurred a few years back, right? Okay, so the concepts that I will use is a minimal USAT is a uniquely satisfiable formula where removing any clause breaks its unique satisfiability. Because I want basically a minimal expression that has that property. I don't want large expressions that contain uniquely satisfiable patterns, because then I get a lot of noise, a lot of non-interesting things. I just want the most interesting parts of the most interesting such patterns. And I will not be generating formulas. I just want the structure. Build instead formula graphs where I abstract away the variable names and use just the pure structure of the SAT expression, right? And of course, a pattern that is basically a formula graph where all the instances of formula graph are uniquely satisfiable expression. Okay, so these are the basic concept. So this is one example of a formula graph that I will use.
Essentially, the isomorphic reduction means all
Yes.
things will be replaced by only one something.
Yes, exactly. So I want to simplify that, have the core thing. So this is an example. So this is an expression, right? So these are the clauses, and the squares are the clauses, and the circles, the black circles, are the variables. They are in pairs, which means one is a variable, one is the negation, but it doesn't really matter which is which. So I have here 5 variables and 4 clauses in this case. And of course, the clause is connected to the literal that is in that clause. Okay, so it's a very simple structure. But this is how I abstract away the variable names or the negations and the isomorphisms and stuff like that, right? Okay, so the problem that I'm solving is, given n and k, find all minimal uniquely satisfiable patterns with n variables and k clauses. So this is how I will slowly make things larger, right? And I tried, of course, a very naive approach, or let's say almost naive, to generate this kind of patterns, and I didn't get very far, because this thing is like double exponential, so it doesn't quite work. So I set for a lazier approach, I want to exploit the power of SAT solvers to actually search for such SAT patterns. So I first had to model my problem as a SAT instance, right? I basically used SMT. So these are SAT modular theories, but I could model all with SAT. I will not bother you with the model itself, but the problem is the model itself is exponential, because to model the unique satisfiability, I have to express that it has to be satisfiable with one set of values and not satisfiable with any other. And this is the exponential part. So I have to specify this. So this is let's say rather large model, but for this for my purposes was good enough, right? And I had to add symmetry breaking constraints because otherwise I didn't get much far, right? Okay, so yeah, I didn't do everything in SMT. I had to do isomorphisms and minimality outside, so as a post-processing step.
3 minutes.
Yeah, thank you. So these are a few examples of the patterns that I managed to find, but altogether the current library looks like this. I managed to go up to 5 variables and 7 clauses. There is an asterisk here because it's not known if it's optimal. I think it's optimal, so I didn't manage to finish the computation. Others are optimal, and the ones in the brackets are the minimal uniquely satisfiable formulas, right? Okay, so in the real-world analysis, the last thing I searched for patterns in 25 SAT instances from SAT 2003 competition. And I created something like this for these 25 instances. So the fingerprints are like this. The rows are an instance, and the columns are the patterns. So whenever a black square is, it means that the pattern 1, for example, is present in instance 1. So this matrix here represents the fingerprints of this instances, and you can see 3 types of behaviors. Basically, some instances have all the patterns, some instances have no patterns, and some have much more interesting behavior. Right. So this is a very rough. You could classify, and you can actually match to certain types of domains this types of fingerprints, right? And this could be used in, let's say, I had all the applications already mentioned before, right? As preprocessing, as classification, or as a help for the SAT solver. So this is some initial work. I hope this. If this doesn't say thank you, then I'm very sorry, but I will blame the artificial. It does. Okay, lucky me. So, thank you very much.
Good one, Uros.
Can I see your left?
And also thanks for the nice presentation. So let us have a round of applause for Uros, please.
This one?
So if you guys have any question for Uros, please. Anyone?
Give an example pattern. Have you shown in the slide what is a pattern?
The pattern is so these are patterns, right? So this is a representation, a graph of a like, yeah.
Anyone else? No? All right, I think. So in which practical purposes this could be used?
Well, I started as an initiative to have a preprocessor for SAT instances. So whenever you find this kind of pattern in an expression that you have to solve, you can add some new clauses to help the SAT solver find the solution. So this is the most naive approach. But there are other things that, as I mentioned, right? So
it's sort of built like a library kind of thing.
yes,
Okay.
exactly. And the next step is use it. I already have some work done, but not in this part yet.
No, so the argument should be how it helps to start from one of your patterns to go to a particular instance, then from other ways. That should be the argument, right? I mean,
That would be another problem to evaluate, I guess. So,
Yeah, I don't know.
pattern where you have to reach. How does it help if it starts from your patterns rather than a generic pattern and go towards that instance?
No, but I start with an instance that I get, and
your ones are uniquely whatever
uniquely satisfiable. Yeah.
That.
Yes.
So why does it help to start from your pattern?
Yeah. Okay. So why does it help? Because if this is uniquely satisfiable, then I know that what the values of these variables has to be. There is no branching. So with the set solver, if it's not uniquely satisfiable, it has to branch on different values. Here, there's no branching. So it's the same.
In terms of time complexity, this should be easily evaluable, right? Because
yes, exactly. You know the values, yes, immediately. But you have to find the pattern. So that's another problem. It's a subgraph isomorphism, basically. Okay.
all right. So thanks, Uras. So we'll look for the next author. I think from IIT Guwahati, someone is the presenter here. Could I get something from the organizers? Should we have it online? Is this online? Can I get a confirmation? Yes, no? Ready? Okay. Pritam Shur. Okay, the next one. Okay, got it. PID 99, which is named as Bayesian optimization for two echelon vehicle routing problem using drone for last mile delivery. Pritam Kumar Shur, Anubroto Noskar, Sunirmal Khadua from Department of Computer Science and Engineering, Government College of Engineering and Textile Technology, Sri Rampur, and the remaining two are from University of Calcutta. Who's the presenter, please? Name? Pritam Kumar Shur. Okay, so Pritam is going to present this paper to us.
Hello. Okay. Thank you for giving me the opportunity to present our paper on Bayesian optimization for two echelon vehicle routing problem using drone for last mile delivery. Myself, Pritam Kumar Shur from Government College of Engineering and Textile Technology, Sri Rampur, and co-authored by Anubroto Noskar and Sunirmal Khadua from University of Calcutta. So last mile parcel delivery is quite some time in research because it is fast, as it does not have to get into the traffic, it fly over the traffic. It's secure because no human intervention is required while it is delivering, and it's green because it does not spread the pollution, right? But also it is limited by battery and carriage capacity, weight capacity. So what we are going to discuss, the problem we address over here is two echelon vehicle routing problem. So there is two echelon. One, the truck is delivering, along with the truck, the drones are also delivering. Okay, and the truck and drone are coordinating so that they are delivering in parallel. So trucks are delivering and the drones are taking off from the truck, delivering, and as well as they meet at some point in the road. So the objective of our work was to minimize the total return time of all the trucks. Okay, so to do so, we have this distribution. So in our problem, we have a distribution hub along with n delivery points denoted by V0 to Vn, where V0 is the distribution hub. And we have all the delivery points are defined in terms of the location, of the delivery point, the parcel weight that is going to be delivered in the delivery point, and service times required to serve that point. For each truck is defined by the set of drone it carries and the weight capacity and the speed of the truck. Similarly, each drone is defined by the weight capacity, the speed of the drone, and the battery capacity B. So we define the time duration after which a truck comes back to the depot delivering all the parcels in this way. That is the total time that is required to cover all the distance it goes, and along with the service time. Okay, and Xij super K denotes the variables. So we have used 4 different variables, decision variables over here. X are the decision variables that denotes whether a truck or drone visits an edge, and Y are the variables that denotes whether the truck or drone serves a particular node. So in the superscript, whenever we have K, it means the kth truck, and whenever we have KD, it means the dth drone of the kth truck. Okay. So with the help of these decision variables, we now define our objective function is the sum, the total return time for all the trucks, that is summed over the K. Okay. And we then model this problem using these variables. So whenever a truck reaches a drone, it will also leave that reaches a node, it will also leave that node, right, and serve that node. So all the summation will be the one. Similarly, whenever a node is served either by a truck or by a drone. Okay, so we have the second constant over there, and similarly the total parcel that a truck can carry, that it delivers, and all the drones that it carrying also delivers can be up to QT, that is the weight capacity of the truck. So that gives us the weight capacity constants of the truck. Now there are some problems with drones, because drones, as we are considering for this problem, drones can take off from any point on the road. Okay, so that, and also it can meet to the truck at any point in the road, and that gives us the that opens up almost infinite options for the drone to take off and land. Okay, so that creates a problem. So to deal with that, what we are doing, so now again, moreover, a drone once delivered in a path, it meets the truck, then it can replace its battery and take another flight to deliver more, to serve more nodes. Okay, so a drone can have multiple flights during the delivery operations. So to identify one flight, one drone flight, we are using the first node that the drone is delivering. Okay, so we identified some of the properties, like since the drone is delivering from a point, so there will be an incoming edge to the node from where the drone is moving fast from the road, but that incoming edge is not from any other node, rather it is from a point, right? So the summation of the incoming edge will be 0, but the drone will be leaving from that node to another node, right? So the leaving node will be summation will be 1. So if this is the first node, okay, of the drone delivery. Similarly, for the last node of the drone flight, it will be leaving to a point, but it will be coming from a point, from a node, right? So the incoming, there will be an incoming edge from a node, but the outgoing edge is not to an edge, right? So the outgoing edge will be to some point. Okay, so that will be there. And similarly, if a node is the single node in a drone flight, so there will be no incoming edge and no outgoing edge from any other nodes. Rather, there will be an incoming edge and outgoing edge from different points in a road. Okay, but the thing is that will be served by the drone. So that in that case, the y variable will be 1. So with the help of this variable, we develop two indicator function. One is to denote the whether the node is the first node of a drone flight, and the second one is to denote the whether the node is the last node of a drone flight. Now with this we also denote this indexing, like if the last node visited till Vj once after a tour started at Vm, so we denote this using this recursive kind of definitions of source. Okay, and with this help of we denote the uh, weight constant for each tour of the drone using the indicator function along with this constant. Okay, next is that is about the drone. What we have next is the launch point. Okay, so drone takes off from any point of launch, right? So how can we define that point? So from Vi to Vj at any point we are defining a variable alpha kd. So that alpha is the fraction of that road segment from where the drone is taking off. Okay, so we define that x, y, and x coordinate and y coordinate of that point, and using that alpha kd, so we have another indicator random indicator function that denotes that whether a point is between a vertex, within an edge. Okay, and using that we denote another function called next node, which actually denotes the when a drone takes off from a point, so what will be the next node that is going to be served by the truck. Okay, so the next node is for the truck after the launch point. Similarly, we have rendezvous point where the drone meets the truck at a point in some different edge. Okay, and similarly, beta is the fraction of time, fraction of path length where the rendezvous point is in the edge. So we have the previous node that denotes the what is the previous node that is served by the truck before reaching the rendezvous point. Okay. So with those help of those functions, what we define the yes. Okay, so let me quickly, so we denote the battery constant. Along with that, we have the synchronization constant. So the synchronization constant basically gives us the time at the same time, so that truck do not have to wait for the drone to retrieve. Okay, so we address this problem using three. There is an algorithm called DTRC algorithm, which is in literature. So we modified some part of it. We used cluster delivery nodes algorithm. So delivery points are divided into k clusters, and cluster heads are distributed throughout the region, and each cluster will be served. Okay, and then we use those cluster delivery nodes, and on each of this cluster we applied the Christopher TSP approximation, and on top of that we also use the local search like 2opt, relocate, and swap, and the best among the result is taken. So this gives us the truck route in each cluster. Okay, and then we replace this is the DTRC algorithm that we referred for our work, and we replace the first line where they use the savings algorithm. We replace with our constructor truck route algorithm, and finally we use this Bayesian optimization to determine the value of alpha KDM. Okay, so initially we use Latin hypercube sampling for generating the candidate set, and then we have some trials to get the value of alpha KDM, and after each trial what happens, we get some value of this objective function along with the alpha, and the value of we are taking the value of alpha that is giving the highest expected improvements, and from that we calculate the meeting point of the drone as well to the trucks. Okay, so we do several trials on top of that, and after that it is giving us the optimized result. Okay, so we ran some experiment on the benchmark instances, and we found that our proposed algorithm works better than the DTRC and the LNS that is applied on the DTRC in the paper, and it gives an average improvement of 9.6%. These are the instances, and in conclusion, we can say that the Bayesian optimization significantly improves the 2VVRD performance effective synchronization of track and down operations are simulated and showed an average improvement of 9.6%. These are the references that we used. Thank you.
Can we go back to last slide, previous? Keep it over here.
This one.
Yeah, keep it over here. Thanks. So let us give a warm round of applause to Pritam. Thank you. So we can afford to take 2 questions at most, if you're interested. Yes.
Yeah, actually, okay. So the name is Bayesian, right?
Bayesian approach.
It's a big name that starts with Bayesian. But where did you apply that Bayesian approach?
Okay, Bayesian approach. Actually, if we look at that, so from where the drone is taking off, and it serves, no, drone is taking off from the truck, yes, and it goes around some of the points, and then it meets to the truck again in different road segments. So we do not know how the function is going. So it is kind of a black box to us, and so we use the Bayesian optimization for that. Bayesian optimization, what it does, it actually improves.
He possibly wants to see the
Algorithm?
Bayesian function that, or the Bayesian
We use the Optuna framework actually for this. Yes.
Bayesian optimizer.
Yes, we use the
Which-
if you see line number
Okay, this
12, sorry, line number 12, we
18 or 12?
12,
Okay,
12,
yeah.
12, yes. We use hyperparameter tuning for alpha KD using Bayesian optimizer.
Hyperparameter tuning, only that part.
Yes, I mean, the details is how the Bayesian optimization is working is given after that. Okay, so we train the.
Yeah, got it. Understood. So anyone else? Anyone interested in asking another question? All right. Thank you, Pridham. Thank you then.
Welcome.
So we would like to invite our next, I think the next talk is online. So we would request the organizers to start with the next presentation. However, I would just read out the title of the talk. So it's PID 88. Title of the talk is Deterministic Integer Sorting on Parallel External Memory Model. So the authors are from IIT Guwahati. Ronojit Chenko is the first author and possibly is going to present. Could we have?
Good afternoon, everyone.
Is this online or is it recording?
Online.
Yes,
Ronojit,
online
are you
presentation.
there?
Yes, sir. I'm audible.
Please start with your presentation. Thanks.
Okay. Just let me share my screen. Good afternoon, everyone. I'm audible. Hello. Am I audible?
You are audible.
Hello.
Please start
Okay,
your
thank you.
presentation.
Okay. Good
So you
afternoon,
have
Professor.
all right. Thanks.
Good afternoon, Professor Partholomik and all others. Myself, Ranjit Senko, and the co-authors, Professor G. Sajid, is my guide from IIT Guwahati. Today, I'm going to present our work, deterministic integer sorting on the parallel external memory model. And the goal of this talk is to explain why integer sorting is important, what is PIM model, what are the algorithmic techniques we use, our deterministic integer sorting algorithms, and finally its complexity and its implications. And this slides actually discuss that. It is my outline of my presentation. First, I discuss briefly motivate the problems and introduce the PM model, and then I'll discuss about what is integer sorting, and how it is different from the comparison-based sorting. And next, I'll discuss about the preliminary parallel techniques our algorithm depends on. These are actually the prefix sum, search algorithm, cross rank, merging, and compact. And then I'll discuss our main algorithm, deterministic PEM algorithm, deterministic integer sorting algorithm on PEM model. It actually, each phase or each iteration consists of two phases. Actually, it is the segment sorting and group creation. And finally, I discussed the complexity result, the comparison with the prior work, and conclude with the future research directions. So let's start. We know that sorting is one of the fundamental computational problem, and it used everywhere, like the database, search engines, graph algorithms, um, scientific computations, and others, and so on, others case also. So we know that it is well known that the comparison based model, the lower bound is n log n, but integer sorting is actually different. If the keys actually consist of integers and drawn from the bounded range, so in that case we can use uh, some we use the arithmetic operations instead of the comparisons. And like that, we can say that the counting sort, radix sort is the example of this case. And we know that in that case, it can able to beat the comparison based sorting, and it can perform near linear time. And most of the cases, these algorithms are fit into, we assume that the algorithms fits in data is fits in the in RAM, but in the modern data set, it is not possible, where the external memory cost is actually dominates. So next is introduce about the PEM model, briefly introduce about the parallel external memory model. Thus, a parallel external memory model is designed to capture the real world scenario. Actually, we have P processors, and each processor has a private cache of size M word, and all processors shares a large external memory. The processors are communicate via the shared external memories, and here the data transfers occurs in form of blocks of size B. And in this model, one parallel I/O steps means each processor can transfer one block between its private cache and the shared external memory. So the dominant cost measures of this model is the total number of parallel I/O steps, and this actually reflects the bottleneck in large-scale systems, where the data movement is important, dominant over the internal computations. And this is the comparison-based sorting. In comparison-based sorting, for comparison-based sorting, the optimal parallel external memory complexity is this much IOs, n by PV log n by B, base n by B. Okay, but in parallel external memory model, the integer sorting is not actually uh, discussed. So this is the our first. There is no deterministic integer sorting algorithm discussed in this PEM model. So it is our first algorithm we have presented. So this is the research gap we have addressed here. And integer sorting, formally we can say that for a given n, we are given n integers from the bounded range 1 to L, where L is represent the largest integer in this set. And our task is to arrange the elements in sorted order. The key differences here versus the comparison-based sorting, we actually don't require, we restricted to the comparisons, restricted to the comparisons, and we can perform the arithmetic and bit level operations. Actually, it actually exploit the uh, performance gains. Okay, expect the performance improvement. Okay, that's performance. We can actually reflect this performance benefit in our PEM model. And key strategies. Our algorithms is we can say that it is a generalizations of the radix sort algorithms, and it consists of number of phases. So each phase has consists of has two different stages are there, segment sort and group creations. So here we know that in each phase we process uh, b bits of window. So we know that the largest integer is L, so it's required log L bits. So total number of iterations of spaces will be required log L by B. And each phases we do the sort segments, and we group the elements based on the current B bits window. And this actually we proceed from the least significant bit position to the most significant bits. That makes our algorithms stable. So this is the preliminary techniques we have used in our algorithms. So first one is the prefix sums. It is one of the core primitives algorithms here. In prefix sums, for a given input array A, it gives the prefix sum gives the cumulative sums of the input array A in the output array D. So here for a particular element in the index position I, it gives the cumulative sums of the input elements from range from index position 1 to I. And here we discussed about the two different algorithms. One is for the first input and the densed input. Both cases it can be performed in linear IOs, and order of n by b steps. And this prefix sum algorithms we use to compute the global rank, and to assign the final output positions, and this helps to in compaction and in grouping. So it is important for the data movement. And next one is the searching. We know that for a sorted array A and an element X, the rank of X in A is defined by the number of elements less than equals to X. So for in parallel external memory model with P processors, it can be computed with this much steps, log n base P plus 1 steps, which is the generalization of the binary search, which is called the PUA search techniques. This searching method, this techniques is used repeatedly in our algorithms. Basically, it is used for the merging and cross-ranking. The next key idea is the cross-ranking, where two sorted arrays given. So here what we'll do for each element in the in array, we compute the rank in the other array and vice versa. And it can be performed in logarithmic parallel steps. The cross rank can be used to partition the data. It can be used to assign the merging boundaries, and it's actually help to parallelize the merging.
Interrupt, Ronajit. You have 3
Yes.
minutes left. Exactly 3 minutes.
Okay, sir. Sorry, sir. So I'm moving, try to finish it early as possible. So parallel merging, here we merge two sorted arrays into single arrays. By this techniques is just by reader selection from the sorted arrays, each sorted arrays in equidistance, and perform the cross ranks of these leaders and partition the input into distinct disjoint sets, and merge these disjoint sets independently. That can be performed into optimally. Okay. And compactions, it is also that move the valid elements so that there is no gaps between the elements, and it can be also computed in linear time. And our algorithms actually it's proceed through a number of steps, number of iterations. To each iteration process b number of bits, okay, and it consists of each iteration phase consists of log L by b steps. The first each iteration consists of segment sorting and group creations. The first I discuss about the segment sorting. In segment sorting, we input array is partitions into alpha blocks. So it is a 2 to the power b blocks, we can say that. If it is the segments are fit into the memory, in that case, it can be sorted using the n by b IOs. Otherwise, it can proceed through the sort cache size elements, and then perform the select the leaders of from this sorted small fragments, and perform the cross rank and do this sort the actual segments. Okay, but to do this, actually, the segment sorting for each segment, it will take this much IOs. But we know that n by b alpha, total number of segments n by b alpha. So it will take n by b into 1 plus alpha by n b IOs. And it is our algorithm segment sorting is stable, which is necessary. And group creation, after performing the segment sorting, actually we select the elements based on the current b bits window or elements. Actually, here we create the 2 to the power b groups. To the power b groups for after in here in this group creation phase,
Ronoji,
we actually
sorry to interrupt once
compute the
again.
group
I would
frequency.
request you to wind up your talk presentation in a few seconds, please.
Okay, so total first final complexities, IO complexities is this much IOs n by b, which is optimal up to a logarithmic factor, and which takes this much parallel steps. If we take alpha is equal to m squared by b squared, and some this is what is the comparisons with the it can be set deterministics. It's use the practical primitives techniques, and we avoid the Icaa sorting, which is the which is impractical. Okay, so our algorithm is better in that case. And conclusion, it is deterministics, and it is optimal with up to log factor. And future work, we can implement this cache oblivious design of these randomized algorithms also, and extend to extra selection and priority queue. And this is sorry. Thank you for your kind attention, and I'll be glad to take in questions from the audience.
Right. So let's thank Ronojit. Let's give him a warm round of applause, please. Thank you.
Thank you, thanks.
So now we would like to invite maybe 2 questions.
Okay.
Anyone interested in asking any question? So maybe I can ask a question. Ronojit, are you online?
Yes, yes. Ask. You're audible, sir. Tell me.
Oh, I'm not really aware of this line of work though, but I was wondering if you have done any experimental validation or something like that, or if there are existing benchmarks
Sorry to
on which
interrupt you.
maybe
You
such
actually
things are
voice is
done.
breaking, sir.
I can't,
Your
you are
voice is breaking,
inaudible.
sir. Hello? Hello?
Maybe not me.
Your voice is breaking, sir.
I asked. Audible to you?
You're audible, but your voice is lagging actually. That's the problem, sir. It is not clear to me.
Could you please
Sorry.
write this question maybe for him? So I'm not aware of this parallel external memory models.
Yes.
However, my question is that did you perform any experiment in order to validate the results, or are there existing benchmarks on which people have already done similar things and you are doing something new? Did you perform experimental validations to see that your method is improved than the others?
Okay, my actually is total theoretical from theoretical computations background. So, okay, so everything is based on proof based. Okay, we have proved based on this whatever algorithm existing comparison-based algorithm is presented
got.
in this.
Okay. So anyone else?
same model.
Anyone would like to ask a question? No? No one? All right. So we would like to end this session. All right. Thank you very much, Ranjit.
So welcome, sir. Thank you, sir.
Thanks, the organizers. I thank the organizers for giving me this opportunity to session this to chair this session. Thank you.
Welcome.
Thank you so much for chairing this session. And I would request Dr. Joydeep Das to please felicitate our session chair. So we'll begin with the second technical session of this evening. It's on track B, AI and machine learning. There are 5 papers, 2 of which are online and 3 are offline. And we request each of the presenters to be please ready. You will have 12 minutes for presentation and 3 minutes for Q&A. We are honored to have with us Dr. B. Uma Shankar to chair this session. Dr. Shankar is an ex-head and professor of the Machine Intelligence Unit at the Indian Statistical Institute, Kolkata. His research interests include pattern recognition, machine learning, deep learning, image processing, analysis of remotely sensed images, soft computing, fuzzy sets, rough sets, and neural networks. He has already published more than 70 research papers in internationally reputed journals and conferences, and a few book articles in edited books. He serves as a reviewer for international journals and conferences, is a member of the program committee and the organizing committee of many national and international conferences. He is a senior member of IEEE and International Rough Set Society, life member of ISI Kolkata and IUPRAI. Dear sir, handing over the session to you.
Right? Can you hear me? Yeah. I welcome you all to this last session. The first lecture is by freshness monitoring and self-life estimation of. Okay. Hello. I think the first lecture is PID number
Hello.
25, freshness monitoring and self-life estimation of bread by Nandini D and DS Guru and Neeta KN and Kavya KN from University of Mysore, I think. University of Mysore. Can I have?
Good evening,
Hello?
sir. Good evening, one and all. Am I audible?
It was not audible actually.
Hello. Now it is audible? Okay.
Yes, sir.
This is PID
It's audible.
25. The
Yes, sir.
title of the talk is Freshness Monitoring and Self-Life Estimation of Bread. By who will be presenting?
Sir, this is Nandini.
Oh, Nandini D.
I will be presenting.
Nandini D and
Yes, sir.
others.
Nandini D.
It is written by others from University of Mysore. Okay, you can
Yes,
start
sir.
now.
Yes, sir.
Start now.
Okay, I'll be sharing my screen right now. Okay. So, is that my screen visible? Am I audible? May I start my presentation right now? Yes.
Hear me?
Okay. Am I audible, sir? Am I audible, sir?
Audible, you can start now.
Okay, fine. Good evening, everyone. I am Nandini D, research scholar from Department of Studies in Computer Science, University of Mysore. My paper ID is 25, entitled as Freshness Monitoring and Shelf Life Estimation of Bread. So, coming to the introduction, as we all know that bread is most widely consumed baked food worldwide, and quality evaluation of bread is very much essential. Yeah, in traditionally, the evaluation of bread is in terms of the physical properties and sensory attributes, and there would be a set of panel members. They would be evaluating the bread quality, but this is inconsistent and it requires a manual power. Later, as the artificial intelligence machine learnings evolve, many of the studies have reported towards the quality evaluation and freshness monitoring of the bread. So here, with respect to the literature survey, we have read some of the articles, and there they have reported towards the effect importance of quality evaluation of bread, and some of the studies they have used the statistical analysis towards the sensory and the physical attributes of the bread. And then some of the studies they have also reported towards the flour quality and the quality of the bread on with the ingredients data and so on. With respect to the literature survey, the major study, that is Kavita et al., have investigated the quality of the bread through the images with the set of texture features with the different classifiers. And in one of the studies, they have used the vision transformers for evaluating the bread. In those perspectives, they have evaluated into two class problem, that is edible and inedible bread. With respect to the literature survey, we have found that the existing methods or the reports, they have reported towards the two class problem, and they have evaluated the texture properties, and no work has still now reported towards the day wise classification of the bread, as the days are very important towards the freshness. As and when the days goes on, the bread will be decade towards the end. So with respect to this, we have arrived at set of objectives. For this, we have created our own data set, which consists of the set of breads from day 1 to day 10, and then we have monitored the evaluation from day 1 to day 10 with respect to the quality and the mold formation and other fine grained details. And we have employed a YOLO V11 with the joint segmentation and classification with respect to the freshness monitoring, and we have classified the bread samples. This diagram shows that our proposed model, given a bread, it classifies which day of bread, uh, including the segmentation. So for that, the basic task is the data collection, where this is a description of the data. Here you can see the data, a single piece of bread from day 1 to day 10. So, and we have collected the data from the different bakeries, 20 different bakeries from Mysore, Karnataka, and these are the white bread. And we have collected from each bakery 3 pieces and 6 different orientation, and we have kept the bread, each pieces of bread with the properly labeled, and we have kept it for 10 days, and then we have taken the photos consecutively. These are totally we have arrived at 3600 in images with the different days of bread. And along with that, as we all know that for the YOLO V11, we need annotations and labeling. For that, we have used the polygon based annotations using label me tool, and we have labeled it from day 1 to day 10. And these are the pre-processing and augmentation strategies what we have used. We have used 80% training and 20% for testing. And then this is the sample of data set which looks like this. And the major challenges towards this problem are, we can see the visual differences between the two consecutive storage days are very similar, and it is very difficult to distinguish between the two consecutive classes, and we will be seeing the accuracy with respect to this. And it also the major challenges also involves in variation due to the bakery specific preservatives, and each of the bread will be prepared differently in the different bakeries. So then this is our proposed architecture. In the proposed architecture, we can see that the original data has been labeled, and the JSON file has been annotated, converted into a text format, and the split as 80 and 20 ratio. And then we have segment. We have used a YOLO V11 for both segmentation and the classification. So here the segmentation, we have used the YOLO V11 segmentation.pt weights for this model, and segmentation mask for the bread regions, and day-wise classification pattern. The training enables a model to detect the bread region first and then classifies the bread into day 1 to day 10. So here the two major perspectives comes into picture. One is the role of segmentation and the role of classification of the proposed architecture. In the role of with respect to the segmentation, the YOLO V11 mask prediction branch used for segmentation, and the segmentation isolates the relevant bread regions, and which focuses on the surface texture, cracks and pores, and discoloration, mold growth, and moisture loss. With respect to the pixel level mask, which improves the interoperability and reduces the background interference. Then with respect to the role of classification, the YOLO V11 detection head performs the classification which assigns the bread image to a specific storage days from day 1 to day 10. Based on this, the localized features from the segmented regions are globally and then global context information enables a distinct between the early freshness and late spoilage stages. Towards the summary of the proposed model, which provides a robust end-to-end pipeline, segmentation improves attention to a critical quality indicators, and the classification enables a security day-wise freshness estimation, which is suitable for real-world bakery environment and scalable food quality monitoring. And combining both segmentation and classification, which enables the benefits of focusing on the freshness related clues and the better discrimination between the similar days. And coming to the results and discussion, these are the experimental setup that we have adopted. So these are the technical details, like experimental details. We have used Adam W optimizer with a learning rate of 1e iPhone 4, and we have used cosine learning rate scheduler, and we have used the performance metrics are as mean average precision with a different threshold. So our segmentation model, the proposed model, has a strong segmentation performance, which is of MAP at 0.5 threshold is achieved at 0.965 for both bounding box prediction as well as segmentation mask prediction. And MAP at 0.5 to 0.95 threshold, it is which we have arrived at 0.749, which indicates the robust localization and region level understanding of the bread image, which confirms the suitability of our proposed YOLO V11 for bread freshness analysis. And these are the results in the table 1, which we have showed the performance metrics of the proposed segmentation model, along with that the different MAP curves of the proposed segmentation model. And we have as we also done with the classification, these are the
Can you hear me?
class-wise accuracy and the misclassification. Yes, sir.
Please finish it
Yes, sir.
in 3 minutes.
Okay, okay, fine, sir. Yes. These are the class-wise accuracy and the misclassification analysis. Here in this, we can see that the day one has approximately the background is classification with respect to 0.003 percent, and the major misclassification it is between the day 4, day 5, day 6 and day 7. So these are the early and late days. So misclassification trends mainly between, as I told, it is between 4 to 5. That day 4 is colliding with day 5, and day 5 is colliding with day 6, like this. Because of root causes, gradual freshness degradation and the subtle changes in the crumb structure and crust appearances. And this is a class overall classification result, and we have achieved accuracy of 81% for as a classification performance. So these are the classification curves visualization, and based this is our proposed, and then we have compared our proposed model with respect to other traditional classifiers and the traditional features. We have extracted OCLBP, opposite color local binary pattern features, and we have given this color feature to a local texture feature to the different classifiers like random forest, decision tree and KNN with the and so on. And we have seen that our proposed model works better with compared to other traditional approaches. And with respect to this, we have seen the significance of finding is that we have achieved 81% of day-wise class accuracy with the MAP of 0.965. And along with that, it is enables a non-destructive bread freshness monitoring, which reduces a manual inspection and a human subjectivity, which supports shelf life estimation and the weight reduction, which is applicable for bakery and retail quality controls. In further future, this data set can be expanded to the other bread types, and also we can integrate with the multimodal data, and we can also integrate with the ingredient data to predict the quality of bread. So with this, these are the set of references which we have used. That's thank you so much.
Let us thanks Nandini for interesting presentation on bread freshness. We can have a couple of questions. Can anybody want to ask any questions? If nobody is asking any question, then I can ask one question. This
Yes, sir.
freshness you will check before the expiry of the bread or after the expiry of the bread?
No, sir. We will be classifying, given a bread, we will be classifying it that which day of bread, and we will be categorizing it that if it is within 1 to 3 days, it is eatable, like that. But in further future, we can extend it to other things.
Expiry date of the bread?
No, yes, sir. We have considered the preparation. We have considered the day at which the bread is manufactured. Like, for example, we went to the bakery, and as soon as the bread is prepared, we have taken the bread and we have taken the photos. That is considered as a expiry date, right, sir? That is a day. The day at which the bread is prepared. That is a day 1, day 2, day 3, like that. So we are classifying the bread into a different days. So based on that date, we can say that it is fresh or it is not fresh.
Thank you.
Yes, sir. Thank you so
Yes,
much. And I would like to
Nandini,
thank ICAA for this opportunity to present my paper. Thank you so much.
yes. That is also online, no? Yeah, okay. I am just announcing. The next lecture is PID 26, Robotic Path Planning using PPO based reinforcement learning approach by Arpan Gorai, Anandita Kundu, and Modipa Jana from Vellore Institute of Technology. Who will be presenting?
Sir, I am Anindita Kundu. I will be presenting.
Yeah, introduce yourself and start presenting. You have
Right,
got
sir.
12 minutes. Hello.
Yes, sir. Is my screen visible? Sir, is my screen visible?
Can you hear me?
Yes, I can hear you, sir. I can hear you, sir. Can you hear me?
Introduce yourself and start presenting.
Okay, sir. A very good evening to the session chair, respected dignitaries, professors, and my dear students. I'm Anindita Kundu from VIT Vellore, and I'm here to present a work on robotic path planning using proximal policy optimization, which is a reinforcement learning algorithm. Imagine a robot in a factory. It needs to deliver path from point A to point B, but the environment is constantly changing. Forklifts are moving, workers are walking, machines operating. So this is the reality of modern automation. It is dynamic, unpredictable, and crowded. Hence, dynamic path planning is essential to avoid collision or accidents. Traditional path planners like A* are great when the map doesn't change, but they give you the shortest path. However, if an obstacle moves into that path, the robot has no idea how to react. Artificial potential field is far more reactive in nature. It pushes the robot away from obstacle and pulls it towards the goal. However, it can get trapped in the local minima where the robot oscillates or stops completely. Analytical hierarchy process, or AHP, helps make smart local decisions like should I turn left or right? This is based on factors like the distance to the goal, angular deviation, and safety. But it doesn't learn from the experience. So we have a gap. Classical methods are precise but inflexible. Learning methods are adaptive but can be imprecise locally. So our goal is to combine the best of the both worlds, that is use AHP for local decisions and PPO for strategic global decisions. Now we understand the problem and the limits of the existing methods. So let us look into the proposed hybrid framework. This combines the classical decision making with machine learning. The key idea is that the path planning operates in two levels. Locally, the robot must make fast, safe decisions, that is whether to go left, right, or straight. And this is where AHP excels. Globally, the robot must learn from experience and optimize its overall trajectory, which is handled by the PPO. Here, as shown in the diagram, this is not purely sequential pipeline. AHP generates a set of locally optimal waypoints based upon the distance to the goal, the angular deviation, and the safety. And instead of executing them directly, these candidates are evaluated and passed on to the PPO, which repeatedly evaluates them, whether they align with the efficient long-term strategy or not. PPO decides that, and if required, refines them. Now, this refinement cycle repeats at every step as the robot moves, senses, and replans, enabling the adaptive closed-loop planning in dynamic environment. Together, they produce behavior that is both reactive as well as strategic. Now, let's understand the process of AHP in details. AHP evaluates each possible next move against the three key criteria, that is distance to the goal, angular efficiency, and safety margin. These parameters are scored and weighted using this scoring equation. Each candidate solution gets a score that is weighted sum of its performance on distance to the goal, angular deviation, and safety. The weights here are critical and they tell us more about what is important in a scenario. These weights are determined using a pairwise comparison matrix where each criteria is compared against every other. For example, is distance more important than safety? How much more? So our initial matrix validated for consistency and gave us weights where distance was most important, followed by the safety and then the angle. But we didn't stop there. Through simulation, we empirically refined these weights as happens in the real world. And as in the real world, relationship between the safety and the distance is not linear. So getting too close to an obstacle is disproportionately risky. So our final weights reflect this practical insight. Distance is the strongest driver, as we can see here, but safety acts as the critical guardrail. Once AHP picks the local best candidate solution, it is passed to the PPO module. The PPO then decides whether this set of waypoints generated by the AHP fits the best long-term strategy or not. This local multi-criteria evaluation is what gives our system the precision and safety. Pure RL algorithms might miss subtle, immediate dangers. AHP ensures every local decision is explainable, weighted, and safety conscious before any global optimization happens. So AHP gives us a smart, safe, local suggestion. Now, if AHP happens to be our local tactician, then PPO is our global strategist. While AHP asks, what is the best next step? PPO asks, what's the best series of steps to reach the goal efficiently and safely, even if the environment changes? At each step, PPO considers a state vector that includes robot's current position, the goal location, and a dynamic map of obstacles. This full context awareness is what allows for truly adaptive planning. The core of PPO is a policy network which has learned through trial and error in simulation and is based on actions that lead to the highest rewards. It takes the current state and generates a probability distribution over the next possible set of waypoints, which are selected from AHP's pre-vetted candidates. Training RL agents can be unstable. One bad update can ruin the policy. Hence, we have used clipped PPO. It limits how much a policy can change from one update to the next. It's like putting guardrails on learning, thereby preventing catastrophic mistakes that could lead to collision in the real world. This makes the training robust and safe. A custom reward function teaches the robot what our priorities are. A strong positive reward alpha for moving towards the goal, a small penalty beta for turning too much, thereby allowing flexible maneuvering, a significant penalty gamma for getting too close to the obstacles. This is acting as our safety enforcer, and a tiny penalty delta for distance traveled, which prevents endless wandering without exploration. So at each step, AHP proposes several good local moves, and PPO evaluates them not just for their immediate benefit, but for how they fit into the optimal long-term path. Accordingly, it might just adjust AHP's top choice slightly, or even choose a different candidate. PPO provides what AHP lacks, that is long horizon optimization and the ability to learn from interaction. But it does so by building upon AHP's structured, safe local foundation. This prevents PPO from making reckless, short-sighted decisions. Together, they achieve a balance of local safety and global intelligence that neither one could achieve alone. We have evaluated our approach in 3 static environments: a simple 4-obstacle layout for basic efficiency, a 9-obstacle layout for narrow corridors to test precision, and a realistic smart factory map based on Hyundai's e-Forest to assess the real-world robustness. As the results have been compared, to with two strong hybrid baselines from the literature, the AHP A-star and the APF A-star. Performance is measured with respect to an objective score. The equation is given here, which is a function of length. Length means the path length, represented by D, the angular deviation A, and the safety margin S. The PPO agent is trained using curriculum learning and then tested on completely unseen maps. Looking at the results, it is obvious that in the 4-obstacle scenario, you can see that the AHP PPO is given by the blue line. It appears to be producing a near straight line, while the baselines oscillate or detour. In the 9-obstacle scenario, the AHP PPO is represented by the red line. It moves smoothly through the narrow corridors, while the others zigzag. In the factory environment, AHP PPO, again the red line, remains relatively stable and safe near the machinery, where the reactive methods struggle. These smoother paths mean lower energy use, less wear and tear, and safer operation, showing how AHP's local precision and PPO's global foresight can work together. After thousands of simulations across all 3 environments, the results are clear. Our proposed AHP PPO framework consistently outperformed the established hybrid benchmarks across every key metric. In the simple 4-obstacle case, the AHP PPO finds the shortest path and achieves zero angular deviation, which means near straight motion. The AHP A-star introduces unnecessary turns, and the APF A-star takes long winding paths. In the dense 9-obstacle scenario, the adaptability becomes critical. AHP PPO again maintains the shortest, smoothest path, while AHP A star exhibits extreme angular oscillations and APF A star detours through corridors. PPO's global planning avoids these local zigzags. In the smart factory map, AHP PPO remains both efficient and safe, while the reactive methods cut corners near machinery. Across the 1,000 randomized trials, AHP PPO reaches the goal safely in about 95.3% of the cases. These results confirm our hypothesis that combining AHP with PPO is going to be providing us with a fundamentally superior path planner. So far, the AHP PPO has shown strong performance in the static environment, but the real challenge in the industry is in handling unexpected changes, that is, moving obstacles or humans entering the search space. So to test this, we built an interactive simulation where the obstacles move unpredictably in real time using sliders with no prior knowledge given to the planner. When the obstacle suddenly blocks the planned path, then automatically the AHP PPO, instead of stopping or replanning from scratch, adjusts its trajectory smoothly while maintaining a safe clearance and continuing towards the goal. This behavior isn't simple reaction. It's basically from the PPO, which has learned from thousands of simulation how to adapt early and efficiently. And AHP ensures that the adjusted step remains locally safe. Smooth adaptation means predictable motion, lower energy use, and safer operation around humans. So traditional methods struggle here. AHP A star must stop and replan. APF A star often oscillates near the moving obstacles. Our hybrid approach combines global foresight with the local responsiveness.
Did it in 1 minute.
Yes.
Yeah.
Hello?
It's all right. Complete
Okay,
it.
okay, sir. Thus, in this work, we have developed a novel hybrid AHP PPO framework that provides about 95.3% success rate in dynamic environment. This ensures safer human-robot collaboration in the industrial settings with reduced energy consumption and higher operational efficiency with shorter adaptive path. The limitation of this work is the response time. It is in the order of seconds. We have further updated this model after this work using the PPO with improved dynamic window approach with chirp, which is giving us a response time of in the order of milliseconds. And in future, we want to reduce the response time even further because in practical environment, the requirement is in the order of fractions of milliseconds or rather nanoseconds. So also, we are in the process of testing it out in the 3D environment using drones. And this improved framework is to be applied in a swarm drone environment as well. So these are the references that we have cited. Thank you, sir.
Nandini, for very interesting presentation on this PPO-based robot planning. We can have a couple of questions if anybody is interested to ask. Is anybody interested? Yeah. Somebody. Hello.
Yes, sir.
Hello.
Yes, I can hear you, sir.
Hear the question?
I cannot hear the question, but I can hear your voice, sir.
Can you hear me now?
Yes, I can hear now.
And was you have in the penalty reward function, you have the one term related to distance traveled so far, right?
Yes.
And
Yes,
there
sir.
you are
Distance to the
using
goal, sir, not
static
distance traveled. Distance to the goal.
over. There's one component, third component was distance traveled so far.
Yes, sir. The distance, not the traveled. I have considered the distance to the goal.
No, the third term.
Just a minute, sir.
Third
Let me
term.
get to the slide. Objective.
Can you just check that?
Yes, sir.
Yeah.
Here I have
previous one.
three parameters, sir. This D here indicates the distance to the goal. This S here is the safety parameter, and A here is the angular deviation.
Yes, slide, previous slide.
We did not consider the distance from the source or.
Can you hear? Reward function. Reward function. Reward function.
Yes, reward function, sir. This one.
The last one is distance
Yes,
traveled.
yes, distance traveled. Yes, sir. Yes, sir.
Throughout. Is it, will the result change if I change the delta along with the distance travel? Suppose I have a threshold, the distance should not be beyond maximum. So ideally, we should have delta more like an impulse function, right?
Yes. But this penalty that we have considered, this delta value, we have considered it to be very small because we are trying to optimize the safety of the robot as well. It should not go and hit a particular object while a particular obstacle while passing by it. To maintain that safety, if it has to travel a little more distance, we are ready to accept that. So we are bothered about the robot safety as well as the distance. So here we have kept this delta as a small parameter. But if we want to change this particular delta value, obviously the result will be affected.
Okay.
Can you hear me?
Yes, yes, sir.
Consider this localization and mapping in your path planning.
Yes, sir.
Is it simultaneous localization and mapping?
Yes, sir. In the runtime, it is doing the localization and mapping.
Okay. Thank you. Thank you. Thank you. Thank you. Let us thank.
Okay. Thank you, sir.
What is the next one? No? Okay. So the next lecture will be PID 73, multi-head, multi-latent attention, an efficient approach to realize a low resource transformer architecture by Sautwik Das and Arnab Santra. Who will be presenting? Sautwik Das? Yeah. Sautwik Das will be presenting.
Hello.
Yeah, kindly complete it in 12 minutes. So
Yeah.
you can have a couple of.
I am audible, right? They start? So last Christmas, I went to a hackathon where, while trying to integrate an LLM into the prototype of my product, I ran an LLM locally on my laptop that was too large for it to handle. The next moment, the screen went blank and my laptop crashed. I realized that that my laptop didn't have enough resources to handle this LLM. This experience led me to write this research paper, Multi-Head, Multi-Latent Attention, an efficient approach to realize a low-resource transformer architecture, authored by me, Sautwik Das, and my co-author, Arnab Santra. Both of us are final year BTech CSE students at Heritage Institute of Technology. So let's get started with this paper. Yes. Okay, thank you. Thank you. So, as we know, attention mechanisms, particularly multi-head self-attention, has become a cornerstone of deep learning and the driving force to progress in NLP, computer vision, etc. Its ability to capture long-range dependencies and contextual relationship has led to major performance gains across diverse tasks. In multi-head self-attention, each head learns a separate key query interactions and aggregates the values, enabling diverse attention patterns. But this comes at a high computational and memory cost, making training and deployment highly challenging in low resource environment. Recent approach to alleviate this bottleneck has been made like multi-head latent attention, linformer, and performer. While linformer and performer suffer from performance and resource trade-offs, multi-head latent attention reduces inference costs, but the training cost remains expensive. To deal with this problem, we proposed a parameter-efficient architecture that maintains baseline performance while significantly reducing the model size. But before exploring this, let's quickly go over the preliminaries like multi-head self-attention and multi-head latent attention. So multi-head self-attention works by projecting the input sequence X into the query key and value using the learned weights WQ, WK, and WV. The attention scores are calculated by performing a dot product between the query and the transposed key matrices. These attention scores are scaled, optionally masked, and passed through a softmax function to compute the attention weights. The output is obtained by multiplying the attention weights with the value matrix. This process is performed for all the heads, and their outputs are concatenated and projected using the learned weight W0 to produce the final context representation. Although this produces a context-rich output, the quadratic complexity in sequence length makes it memory inefficient. Now, multi-head latent attention deals with this problem by introducing a latent space from which the key and values are generated, effectively reducing the number of trainable parameters and reducing the KV cache bottleneck. The query computation is unchanged. The attention weights and context representation in MLA is calculated as in self-attention. Now, on the surface, it seems that we just introduced some more learnable parameters, but by performing some simplification, it can be noticed that we have actually reduced the number of learnable parameters, and this makes the architecture look like this. So although this reduces the size of the KV cache, reducing inference costs, but training cost remains expensive. This leads us to our first proposed architecture, query key weight combination. The main idea behind this is to skip the pre-multiplication step by replacing the two matrices by a shared projection matrix. This also attempts to reduce the parameter count but in practice, we have observed a slight increase in parameter due to the size of the latent space. This leads us to our main proposed architecture, as we have used this as a stepping stone to our main proposed architecture, which is multi-head, multi-latent attention. Here, we introduce a shared compression matrix that first maps the input X into a lower dimensional latent representation L dash. Both the queries and key value latent projections are produced from this compressed representation. In terms of original input can be represented as follows: Q equals to L dash the WQUK, and the LKV can be represented as the L dash WDKV. The attention weights and context representations are calculated as in MSA and MLA. The number of learnable parameters and the optimal value of the DC, which is the size of the compressed latent space, has been calculated there. To evaluate the effectiveness of our proposed multi-head multi-latent attention, we conducted experiments to benchmark summarization on summarization dataset. The dataset we have used is from Kaggle, a news summarizer dataset by S. Bhati has been used. 10% of the dataset was used, from which only the 95th percentile was taken to deal with outliers. 80-20 training and validation split was done. Standard preprocessing steps were applied, including tokenization, lower casing, and truncation of the maximum sequence length to 1934 tokens, which is the dataset's 95th percentile. Now, the training configurations are as follows. We used a single GPU of RTX 3060 12GB to keep the comparison fair. We used a batch size of 20 epochs, a dropout rate of 0.1, embedding size of 256. Each of them had each of the MMLA layer had 4 heads and 4 layers, had a maximum input length of 1024, a maximum output length of 256, and the KV latent size was 128, and the compressed latent size was 64. Although this configuration produces smaller models than standard transformer setups and does not match the industry level performance, we adopted it due to time and computational constraints. Our goal is not a state-of-art results, but a controlled setting to evaluate the efficiency and effectiveness of different attention mechanisms. We have assessed summarization quality with token accuracy, perplexity, and rogue 1, 2, and rogue L. The training efficiency with training time has been evaluated with training time, VRAM usage, and parameters per layer. The results are as follows. The experiment shows a clear difference among the 4 attention mechanisms. MMLA achieved the lowest parameter count at 1,55,648 per layers, the lowest memory usage at 3.6 GBs, and nearly half the training time when compared to multi-head self-attention, demonstrating the efficiency and query and latent compression. Multi-head self-attention remains the most accurate with a token accuracy of 0.3043 and the Rogel score of 0.1465. However, multi-head multi-latent attention was closely behind it, outperforming multi-head latent attention. Its perplexity score is almost comparable to multi-head latent attention, while having half the training time and the parameter count. We have observed that the query key combination version of our architecture has performed poorly, indicating that combining query and key weights cause significant information loss. Multi-head latent attention, while effective at scale, showed limited accuracy in this low resource setup. Overall, multi-head multi-latent attention strikes a strong efficient accuracy balance, cutting training time by about 47% and memory usage by almost 50% compared to multi-head self-attention, while retaining most of the performance. Our proposed idea drastically reduces the model size by introducing a specialized input compression layer while maintaining a competitive accuracy and Rogel score. It also matches the stability and token accuracy of more complex models. It lowers the computational overhead by compressing both queries and KV projections, minimizing the per head cost. While tested on summarization, the architecture is versatile enough to be implemented for diverse tasks. Our future works include implementation of larger models and scaling to larger data sets, deeper and multilingual models. We also plan to integrate them with efficient variants such as performer, linformer, and flash attention. Now let's hope that more research on this topic helps us make the attention mechanism so efficient that I can finally go back and run my LLM on my laptop without it crashing. And on that note, I am ending my presentation. Thank you. So any questions?
We can have a couple of questions.
Relevant research.
Yeah, thank you, sir.
Few things. I saw perplexity score around 85% and all.
Yeah.
More than 80%. So what was the data set that you used? Because
Yes, sir, I can't hear you properly.
perplexity score around 80% that is reported there in your.
Yeah.
So what is the data set that you used? Because when we check the perplexity score of state of the art algorithms, right?
Yeah.
Architectures, they report close to 9 or even less than 9.
Yeah. So the data set we used was a news summarization data set on by S. Bhati from, it was taken from Kaggle. We tested it mostly on news summarization tasks, but it can be applied to various other tasks as it is an modification on the attention mechanism itself.
Right. So few suggestions.
Yes,
There are a lot of industry glue benchmark on which you can apply and see the result. That's one. And in terms of the comparable architecture, there is one paper that is written as lost, which is more like using some kind of lower embedding and things like that. That
Yeah.
could be competitive architecture. You can compare again. That rather than comparing against different variant of the architecture, existing architecture, that could be a
Okay.
good thing. Good
Okay.
work.
Thank you.
Thank you. Is there any other question? Here with the front.
Hello.
Yeah.
So can you go back to your results section?
Yeah.
Yeah. So you have mentioned that you have reduced the parameters to half, which led to the training time being half.
Yeah.
So isn't that like
Yeah, it is being, the training time is being reduced by half while there is no loss of performance, right? So I think that is more efficient than the current
sure,
existing models.
you
Yeah.
can say that. However, I think the parameters per layer results in like the same sort of training time.
Yeah, we have trained with the same number of parameters. Everything else is same, except due to the change in the number in the architecture. Yeah, sorry. Yeah. So the number of learnable parameters in each of the heads have changed. That have been reduced. We have reduced that by half, but the performance has been same now.
Performance has been compared.
So I guess it is more efficient than the pre-existing models.
Sure. Thank you.
Thank you. I have one more question.
Yes, sir.
That validation loss, why that curve is like that? Validation loss, the last.
So it is basically we have plotted these models there.
That is not the right way.
Yeah.
Okay.
I will try to fix it in future works. Thanks, sir.
Who is the next one?
Please.
Next paper is PID number 80. Alertify, an AI-driven multimodal social media framework for real-time disaster monitoring and response by Mohit Jana, Alok Raj, and Priyanshu Pilaniwala. Okay, Kushi Bharti and Ratika Manna and Dishika Junjunwala, Smita Das and Jhalak Datta. Yourself is?
Mohit.
Mohit. Okay, Mohit will be presenting this one.
Okay. So, good evening, respected session chair, all the dignities, teachers, and my dear friends present here. Today, I, Mohit Jaina, a final year student of Computer Science Engineering Department at Heritage Institute of Technology, is honored to present before you our research paper with PID 80. The title of the paper goes, Okay. The title of the paper is Alertify, an AI-driven multimodal social media framework for real-time disaster monitoring and response. So moving on to the presentation, as you can see, this would be the table of contents and how the flow of the presentation is. So moving on to the abstract. India faces many natural disasters every year, and during these events, a huge amount of information appears on social media in different languages and formats. This information is useful, but it becomes very difficult to quickly filter what is real, relevant, and reliable. To solve this problem, we have developed Alertify, an AI-based system that can take the unstructured social media news and data and turn it into clear, actionable disaster intelligence. Now, moving on to the introduction and motivation behind our work, let us try to understand what is the problem big enough, and how growing social media platforms play a crucial role in providing real-time situational updates during disastrous event. So, India is one of the most disaster-prone countries in the world due to its geography, population density, and climatic risk. The National Disaster Management Authority reports that 58.6% of our land is prone to earthquakes, 12% to floods, and 68% to droughts, and about 5,700 kilometers of the coastline is exposed to cyclones and to tsunamis. Between the year 2000 and 2019, India faced 321 natural disasters, causing over 1 lakh plus deaths and impacting 1.8 billion people. In 2020 alone, the Assam flood displaced over 5 million people, and the cyclone Amphan caused losses of more than 1 trillion INR, making it one of the costliest cyclone in Indian history. These statistics demonstrate the urgent need for India for a robust, technology-driven solution for disaster preparation, early detection, and rapid response. Now, how social media is playing a role out here. Social networks have a crucial role in Indian disaster events by making the communities act as social sensors. During 2015 Chennai floods, the citizens used Twitter and WhatsApp extensively to share ground level updates, rescue reports, and organize relief distribution. Similarly, during Cyclone Fani in 2019, thousands of social media posts provided real-time situational updates, which were utilized by local authorities and NGOs to plan out rescue operation. The challenge in India lies in managing the overwhelming amount of multilingual and multimodal data, and often unstructured, which requires advanced intelligence system for meaningful interpretation and actionable insights. So moving into the literature review, if you carefully take a look into the table, you can see that the literature review shows how disaster response has evolved throughout the years. In the yearly 2020, highlights the importance of multimodal fusion models. So here basically text and images both are being encoded to make models for disaster prediction. Then from 2021 to 23, if we can see, the focus shifted to real-time monitoring, like methods like edge AI and spatiotemporal models, improving speed and reducing the alert delays. So basically the focus shifted from how to process the data to how fast we can do it. And the research in 2020 to 23 introduces interactive dashboards and spatial clustering, ensuring that data is not just collected, but is actionable for users. The most recent studies from 2024 to 25, as you can see over here, uses advanced transformer-based models and sentiment analysis to automate disaster detection. So overall, the literature shows a clear shift towards faster, smarter, and more automated disaster intelligence system. However, the literature review also highlights certain research gaps and scope of improvement in the domain of disaster management and response. Alertify directly addresses these gaps by enabling real-time streaming and using of multimodal disaster classification system for faster and reliable alerts. So now moving on, we have the proposed methodology. So as you can see, this is basically the overview of how the system works. So the system is completely live and dynamic. It keeps on running, and after specific interval of time, it starts scraping news from all social media platforms, be it Twitter, be it Instagram, be it Facebook. All the news are then passed into our disaster analysis model. We have basically two models. We have splitted the models, so the models are smaller and they give us the results faster. So the first models work is to basically tell us, is to basically flag that whether the news is a disastrous news or not. And the work of the second model is to predict what type of disaster it is and where is the location of the disaster. The details regarding the models are in the upcoming slides. Then what happens if there is any kind of media that is associated with the social media posts, be it any kind of video, be it any kind of picture or audio, that is then passed into our model also to do an audio analysis and video analysis. In the video analysis, we have a complete object detection system. We have thermal mapping, magma mapping, so that we can also get the number of count of victims that might be present in that area. And in the audio analysis part, we are doing a transcription. So basically whatever the people are saying in the video, that gets transcribed. Even if it is in vernacular languages, it gets transcripted. And we also give the audio spectrometry analysis. So basically an audio expert can see from the curves that whether the people are in panic or how is the scenario in that area. Now moving on to the first model.
It's interesting, but you have to finish it in 2 minutes.
Yes, sure, sir. Okay, so talking about the first model is a multi-layer perceptron model. So it has been trained upon a total parameters of 2.4 million parameters. So as you can see, there are basically 4 layers. The 3 layers, these are the 3 dense layers which have neurons of 50, 100, and 50. In these layers, we have used the RLU activation function. There might be a question that why it is not facing from any problem like dying RLU problem. The reason is that because we have less number of layers, that problem generally arises when we have more number of layers. And also since we are using the TF-IDF vectorizer for textual input and it does not generate high negative values, so we don't face that problem. And in the last layer, we have the sigmoid activation function because we require a binary output from the first model to flag it whether it is a disaster or not a disaster. So now moving on to the second model. The second model is a disaster class classification model. So it is basically a soft voting ensemble classifier which comprises of logistic regression, multinomial naive Bayes, and k nearest neighbors. So there might be thing like why soft voting, why not hard voting? So what is the basic reason about it? Because in hard voting, the confidence of each classifier is not taken. Suppose if my model logistic regression flags it as flood, my multinomial naive Bayes flags it at flood, and my k nearest neighbors flags that no, it's an earthquake. But the confidence of these two models are lesser than this model. But due to hard voting nature, since flood gets 2 points, so that gets flagged as flood. So to address that problem, we have used a soft voting ensemble classifier to predict. And moving on, these are the results. And this is basically the data set. The data set split shows how many number of earthquakes we have, floods, accident, fire, and cyclone. Presently, these are the classes that we are considering. Most of them are natural disasters. In future, we have a plan of going into artificial disasters or man-made disasters also. So the data set, the primary data set is a Kaggle data set, which comprises over 11,000 tweets that are taken from disaster related news. Then it has been also like, it is a combination of multiple data sets. So the supplementary data sets is the EMDTA public disaster database. And then we have customly annotated it also. Now moving on, these are the results of our model. This is the confusion matrix and training curve for the first model. And this is the confusion matrix for the second model. The first model achieves an overall accuracy of 84.346%. And the second one achieves about 88.896% accuracy. Now moving on, the comparative analysis. So what presently exists that doesn't caters everything that is required by a disaster management agency to solve these kind of problems. Some are taking only text, some are only going for images. But Alertify is a single system which takes everything into account, be it text, be it audio, be it video, or even the geographical location and the geographical environmental condition in that area. As we move on to the next slides where we have snapshot of the working system, we will understand that it is basically a pipeline. Whenever there is any disaster that is reported to us, it goes through a pipeline of different stages where we can actually validate whether the news is correct or not. And also the system is tested live dynamically in day-to-day lives. So it is not like a stipulated environment where we test. It is a real-time dynamic system. So it completely takes the things and does. So moving on, we have the snapshots of the working system. As you can see, at least 60 people died and have been injured in Nepal due to devastating floods. The system flags it like this, tells us the class and the location. As you can see, this is the image of the actual image that got posted upon Twitter, and how our system identifies it and rectifies that it is identifies that it is an disaster. Moving on, as I said, that it is a complete system. So we have different tabs for the audio analysis, for video analysis, for the geographical information, the real-time geographical information, so that to validate the news that we are getting. Now, moving on, what are the future goals? As I already said, implement continual learning to allow Alertify to automatically adapt to new disasters. And mostly the last 2 points, which is like perform real-time development deployments and evaluate system performing during live disaster events. And these are certain references that we have taken. Um, okay, it was a thank you slide. So
Okay,
thank you, and
Okay,
hope you
we
like.
thank him for a very interesting and important application. You can have one question because already time. Just one question, if anybody is interested in asking.
Yes, sure.
So we didn't see those results here. And second thing is how do you classify? I mean, I do know that news that you are getting, what is posting, whether those are correct or not. There are
Okay.
protocols.
So if you just see the system, what happens, the system is live. So it is continuously going to social media platforms, Twitter, Facebook, and scraping out newses from different platforms. Like there are certain public channels like the NDTV, be it any news or be it any kind of disaster keywords. We are continuously looking for those kind of news if there is any in the social media. If it is, then it is pushed into our system, the news. Then what happens, the models, the two models that we have developed, it from the text which is written in the post, we basically identify the type of disaster and the location of disaster. Now, what happens if there is from the text, we can't just identify that, we just can't confirm it that it is a disaster or not. For that, what we are doing, if there is any kind of video or audio that is associated or that is like you have uploaded it with the post, that gets automatically fetched by our system, and that is processed into the video analysis and audio analysis tabs. So it basically does a audio and video evaluation of that area also. And talking about, as you said, that it's not about just classifying, it also about how to inform the local authorities, how to actually validate it. For that, we have the geographic analysis tab. So what happens, suppose if I get a news in social media that there has been an earthquake in Patna and some peoples have died. So I can do a textual analysis, the models will flag it, then I can actually go and see if there is any kind of video or audio associated with it, and then I can actually go to my geographic analysis tab, and here we have an earthquake predictor system. So we can actually get that, is there any kind of geographic symptoms that we see, like has there been any earthquake in near to those regions which validate that these kind of natural phenomena can occur in the nearby region.
Okay, thanks, I think.
Okay, thank you.
Thank you. Thank you. Let's start. We have come to the last lecture of today's presentations. It is PID 101 by Mako Sync, multi-agent colony optimization for synchronized arrival condition, and will be presented by Vidit Garg, I think. It will be online. The paper is written by Vidit Garg, Swapnil Mone, and Suman Kundu from IIT Jodhpur. Vidit Garg, are you there? Hello?
Hello? Hello? Hello.
Hello?
I'm audible?
Can you? Oh, Sapnil Mane. Okay. Sapnil, can you hear me?
Yes, I'm audible. You are audible.
You can present it. Please complete it in 12 minutes. Huh? We will have a couple of questions after that.
Sure. Yeah. Thank you. Second. Yeah. Good evening, all. I'm Swapnil Mane. Here I'm presenting our work on a Mako sync, a multi-agent and colony optimization for synchronized arrival coordination with Vidit Garg and Dr. Suman Kundu from IIT Jodhpur. So the focus of this paper is on coordinating multiple agents so that they arrive together in time, not just efficiently in a distance. So why we require the synchronized arrival matters. So this is our motivation, as in many real world scenario, multi-agent task arriving at the same time is more important than taking the shortest path. So let's take one real world example where coordinated military strikes has been conducted. So there is a one targeted location where there is a one, the map is represented in the graph. The node is represented as a location and the age is represented as the path to reach that particular location. So there are multiple coordinates out there. So the each of these agents, we represented as in this agent as an agent, that is a naval and aerial and the ground forces as an one agents, and they have to reach or target or strike on the targeted location at a same time. So they have to target on a location and within a same time actually. So instead of the shortest pass, along with we have to strike on the strike in the same time actually. This is important actually because even in small timing differences can lead to mission failure or reduced effectiveness. This motivates the need for algorithms that explicitly handle the temporal coordination. So there are similar other applications as well: emergency responses responses units, UAV, or robot swarms as well. Okay. So in line of this work, there are some existing works. There is an and colony optimization, which is and more efficient for the optimizing the shortest paths, finding the shortest path. So in the end colony optimization, that is an ACO, which is mostly uh, built for, which is actually principally built for optimizing the minimum path cost or distances. When extended to multiple agents, it often produces solution where agents arrive at different or very um, diverse timestamps. So there is a lack of SEO methods explicitly optimizes for temporal synchronization. That is, and there is a difference between the arrival time of the all of these agents should be minimum. In other coordination methods like consensus or control-based approaches usually requires continuous or communications uh, centralized planning. These assumptions which not hold the advisor or communication constrained environments. So there are extensive work on ACO and multi-agent coordinations, synchronized arrival. But the synchronized arrival has received a little attention nowadays. So existing multi-agent ACO approaches mainly focus on parallel optimization or distributed problem solving. So there are limited works on explicitly optimizing for arrival time alignment. That is synchronizing the arrival time to the destination. So these gaps motivates our work. So considering these gaps, we have proposed a Mako sync, which is an multi-agent and colony optimization for synchronized arrival coordination. The key idea behind the Mako sync is a simple but effective. Instead of optimizing shortest paths, we optimize arrival time synchronization. Agents coordinate implicitly through pheromone updates, and no direct communication should be there actually. So the ant colony optimization, it is an bio-inspired optimization technique based on how ants find shortest path using the pheromone trails actually. So they are trying to explore the multiple paths and they are depositing their pheromone on their path. And highest pheromone concentration in any paths, that means those paths is highly likely to shortest path toward the destination food. So artificial ants explore solutions and reinforce good paths with the pheromones, making them more likely to be chosen in future iteration. Over time, this collective learning leads to high quality solution without centralized control. So in our macro sync uses a shared global pheromone matrix across all agents. Each agent is independently construct its path using the shared information. Okay. So we model the environment in as a weighted graph. Multiple agents start from a different nodes. These are the starting positions, and which also share the common destination, which belongs to the overall vertices. So agents may have different speeds and making synchronize that makes synchronization even more harder. So our ultimate aim of this macro sync is to minimize the variance of arrival times across the all agents. So this is the difference between the overall time span of the all agents and this the mean of the all of the agents arrival times, and this is the single arrival time of the each of the agents. So this arrival time we have calculated using the cost of that particular path divided by the speed of that particular agent. So this is the mean of the all of these arrival time of all agents. Okay. Yeah. So to transfer from or to move from one node to another node or to finding a path, agents are considered three factors actually. So we have introduced a three factor. The first one is an pheromone concentration, which is an pheromone strength reflects the past successful coordination. Second one is an heuristic information, which captures the age cost. And the third one is a temporal coordination factor, which introduces the temporal synchronization. So here, this factor this time factor agents to means this factor biases agents towards each choices that bring their arrival time closer to the group target. So here the target T target is an previous arrival time, average arrival time, and this estimated timestamp is an for each of the agent we have computed the estimated timestamp, which is based on the cost of that up to now how much the cost has been traveled and the new age weight and the speed of that particular agent. So this we have introduced in the pheromone or probability estimation. As we have saw previously that in transition probability we introduce a pheromone factor. So how the pheromone factor or is updating. So here this is the new pheromone is updating in newer, and we have incorporated the previous pheromone along with the evaporation rate, and also we have incorporated the pheromone along with the temporal clustering density. So here how the phi has been calculated here. So that is an it takes the how much the difference between the current estimated timestamp with the other agents, and also the here is an clustering density, which is and how many number of or total number of nodes, total number of agents which has been near to near to the estimated time or targeted time actually. So these are the divided which are the divided by the total number of agents. So this we actually updating our pheromone weights by how well an agent's arrival time aligns with the others. And second is an agent's arriving close in time reinforce the same paths more strongly. Over iteration, this naturally pulls agents towards the synchronized arrivals. Okay. Yeah. So this is the flow of the microsync algorithm. So first we have initialized the pheromone with the one value, then that is best synchronized score, which is zero
Swapnil,
initially,
can you
and
complete it?
yeah, sure. So second one, we have further we constructed a path that is we are finding the optimal path based on the pheromone and the transition probability as we have discussed earlier. And then we have computed the arrival times and their variances. Based on that, we are trying to update the pheromone based on our previously discussed equation. So these are the evaluation matrices. To evaluate the coordination quality, we use the following matrices. The arrival time variance captures the how spread out arrives are. Synchronization rate measures how many agents arrive within a tolerance window. And the synchronization scores combine both aspects into a single metric, which is and synchronization rate and arrival score variable. So we have evaluated our macro sync against the related baseline, which is, and we have incorporated traditional ACO with the a synchronized manner, and which also includes the other baseline, which is an persistent exploration practical SOM optimization, which is a method from UAV trajectory planning. And we have experimented on two benchmark data set of moving AI lab benchmarks, we used a random and structured environment graph. And also we have experimented with the synthetic data we have created by random graphs. So in the results, we found that MacoSync significantly outperforms the baselines. That is, and we observed that up to 23.9 times improvement over the synchronization score over the base baseline. And further, also arrival time variance is reduced by a factor of 6.8 with respect to the best baseline. So yeah, so the next one, we have also incorporated a tactical coordination, which we have incorporated synthetic data we generated using the Renderer-Sreni graph, random graph. So here we have computed or evaluated the model with the baseline models, and we found that over the consist of the period or matrix, the macrosyncs performs well with respect to the baselines. Okay. So further, we have did ablation by removing the or disabling the density-aware pheromone update, which leads to an even larger degradation. After removing the temporal bias from our transition probability, which is also noticeable drop in the synchronization quality as well. This confirm that the both components are essential and complementary. Together, they enable a stable and stronger temporal coordination. So we have also demonstrated a simulation of this algorithm on a random data set. So here you can see that is a green nodes represented as our agents, which are the starting position of those agents, and their common destination is an yellow node. So you can see the model iteratively trying to do a similar distribution between the all of these three agents actually. So you can see this is the distribution of the orange, green, and blue. So at the end, it optimized to a similar distribution. Yeah. So in the conclusion, we introduce a macro sync, and also we're trying to move towards the optimization focus toward the from shortest spot to arrival time alignment. And also we achieved the significant improvements over the baselines. This also operates without explicit inter-agent communication as well. Yeah. So the source code is available on the GitHub. Yeah. Thank you. I'm happy to take questions.
Thank you, Swapnil Mane, for a nice presentation.
Thank you, sir. Yeah.
I have one question at least. Can anybody wants to ask one question? Hello? Is no questions? So thank you, Swapnil Mane, for your presentation. Everybody is waiting. Pardon? Thank you. Hello,
Okay,
Swapnil.
thank you, sir. Yeah. Thank you, sir. Yeah. Yeah. Thank you.
So we are getting late for the, I think, cultural program. Thank you
Okay.
for giving me this opportunity to session this chair.
Thank you so much, sir, for chairing this session. And I would now request Debranjan sir to kindly felicitate Dr. Umashankarji. A big round of applause, please. Thank you, sirs. As you can see, the QR code for feedback has been uploaded on the screen. Please scan it and give your feedback for today's sessions. So, as you know, the day has ended, but the evening has just begun, and it's time to unwind and relax. We have an amazing cultural evening lined up for you, followed by dinner. Please stay seated. We'll meet back, or we have tea coffee outside. Please feel free to have some tea coffee, and we'll meet back here in 10 minutes' time. Thank you.
Mute